Swayam Prabha. Digital India. Educated India.
Hello. So in the previous class, we were mainly focused on the Navier-Stokes equations. We looked at the convective term versus the diffusion term. That's what we put most of our focus on. We looked at the Reynolds number definition. We looked at the Reynolds experiments, how Reynolds number was a ratio of inertia over viscous, and how that relates to the two terms in the Navier-Stokes equations, the nonlinear term, the convective transport, and the viscous diffusion term. And essentially, the flow or the transition between laminar to turbulent is a balance between convective transport and viscous diffusion. In the same way as Reynolds number is a ratio of inertia over viscous, convective transport balancing between viscous diffusion determines the characteristics of the flow, whether it is laminar or turbulent, or is something in between, like we call it transitional flow. So we looked at how convective transport dominating over viscous diffusion leads to turbulent flow, whereas viscous diffusion dominating over convective transport leads to laminar flow. And we talked about enhanced diffusion being one of the attributes of turbulence. Okay, so we started this class by talking about the despair, right? How it was difficult for scientists to pinpoint and try to understand the different aspects of turbulence. It was hard. Then we talked about why study turbulence. And then we looked at some certain characteristics of turbulence, especially with regard to the Navier-Stokes equations. So now we have a basic idea about what some of the attributes are. Let's look at the attributes in a little bit more formal manner. But before that, let us see if we can define turbulence. We looked at some descriptions of turbulence earlier, and the Navier-Stokes equations is actually the most modern description, mathematical description of turbulence. So that's what led us to the Reynolds number and the balance between convective transport and viscous diffusion. But now we have gotten all that down. Can we try to define turbulence? Every concept needs a definition, right? So if we can define it, that means we are able to understand it very well. But are we able to understand turbulence very well? So in that case, will we be able to define turbulence? So here again, I do want to give some historical context. Many people have made an attempt to define turbulence. One of the first definitions was from Richardson. So Richardson sort of wrote a little bit of a poem on turbulence. Maybe he meant it as a definition. So as you will see, it was mostly based on his observations, kind of like what Da Vinci did. He said, big walls have little walls which feed on their velocity, and little walls have lesser walls, and so on to viscosity. So here, what he is describing as walls, one can take a guess that he's talking about the eddies. So you have large eddies or large scales, and they have some small scales, small walls, small eddies, small scales, which feed on their velocity, meaning the velocity is what is giving the energy to the large scales, which is transferring the energy to the small scales. And the little walls have lesser walls, meaning the small scales are breaking up into even smaller scales, and so on. it keeps breaking up, and so on to viscosity. So that means as you get to the smaller scale, eventually they sort of disappear and disappear is not the technical word, dissipate is the word. They dissipate due to viscosity. That is essentially what it's saying. We can say all that now because we have a fair idea of how the turbulence is generated and how the energy dissipates from the large scales to the small scales. So we are able to say that. But that is what he is referring to. That was what he was referring to in 1922. So you will see that as we move on, we'll look at other people who have tried to define turbulence. There's no good definition of turbulence. And at this point, we have gotten to a point where maybe there is no formal definition of turbulence like you have for a lot of other phenomena that you see out there. This is again pointing towards the fact that it really is one of the last unsolved problems in classical physics. Moving on, let's look at the next definition. Okay, von Karman. He quotes Taylor and came up with the following definition. Turbulence is an irregular motion which in general makes its appearance in fluids, of course, gaseous or liquid, when they flow past solid surfaces or even when neighboring streams of the same fluid flow past or over one another. So what he is referring to is the fact that turbulence is an irregular motion as opposed to laminar flow where it is regular, it's smooth flow. Turbulence, the irregularity is what makes up the turbulence. That's essentially what he's saying. But he's also saying that it occurs in fluids. It occurs when fluid flows over flat plates, say for example, some kind of solid surface, and also when two fluids flow over each other. So that was von Karman's definition. The irregularity is what he focused on. So the first definition was Richardson's, right? And here, remember, he had a lot more information in his definition. The fact that he was talking about the energy cascade is the important point here. What he's essentially saying is that the mechanical energy is injected into the fluid at the large length scales. That is what he means by feed on their velocity. At the large length scales, and then the energy undergoes a cascade. The little volts have lesser volts. So that cascade process is where the large scales break up into small scales, break up into even smaller scales, so on and so forth until they get to the smaller scales where it dissipates due to the viscosity. Okay. Now, keep in mind when we talk about the smaller scales, okay, I want to take you back to the previous class where I talked about the smaller scales are still at a point where the smaller scales means they are small enough that the continuum hypothesis is still valid. Okay, we are not talking about molecular scales. We are talking about small scales where the continuum hypothesis is still valid. Okay, so that is something to keep in mind. But that was Richardson's definition and then Taylor's definition. Now, Heinz, in one of his widely used texts on turbulence, offers another definition. Turbulent fluid motion is an irregular condition of the flow, just like what von Karman did, in which various quantities, he brings in another word here, various quantities show a random variation with time and space coordinates so that statistically distinct average values can be discerned. A random variation. So he said that it is irregular, okay, and we know, right, it is irregular. He says that there is a random variation of time and space coordinates. That is what it looked like to him, that it is random with space and time. Now the question I want to ask here is it really random? Do we absolutely have no idea why it happens? That's what random is, right? Is it really random? So let me keep that question on hold. Okay, we'll try and answer that in this class, in the next few classes, and so on. But the last part of the definition also talks about how statistically distinct average values can be discerned. So even though it is random, what he's saying is that even though it is random, we can actually get definite average values. Average values that are not random. Random values with space and time, but average values which can clearly be discerned. So that was his definition. So I only showed three here, but you will see one of the problems with all those definitions is that it does not offer any precise characterization. Okay, like we have definitions for other phenomena. It does not offer any precise characterization. All these definitions are providing is that based on specific flow conditions, they are describing what the flow is. They might not be offering a precise definition of turbulence. So in that sense, the definition is not telling us when turbulence will or will not occur and to what extent and what intensity. Okay, one can argue that it is probably because of the lack of this precision. Okay, probably because of the lack of the precision, we are not able to understand turbulence to its full extent. And probably that is why we are not able to solve the turbulence problem. Because one can argue that if you don't know what turbulence is, if you cannot define what turbulence is, can you actually solve it in a quantitative sense? Meaning know exactly when it is going to occur, what is going to happen next, at what intensity is it going to happen. Can you actually predict that? Maybe not knowing the definition has something to do with it. So here, Chapman and Toback, what they did is they described the evolution of turbulence as three different eras: the statistical, the structural, and the deterministic. And we'll go over each of these in detail. But you have to understand what these terminologies are. Statistical would mean averages, variances, statistics, right? Structural would mean looking at the structures of turbulence and trying to make sense out of it. Deterministic means you're trying to determine the solution. So, based on these three eras, okay, we now have, and based on observations, experimental observations, and the way and the understanding of turbulence has evolved along these three eras, we now have a more precise and modern definition of turbulence. Okay. So this is the modern definition of turbulence. Turbulence is any chaotic solution through 3D Navier-Stokes equations that is sensitive to initial data and which occurs as a result of successive instabilities of laminar flows as a bifurcation parameter is increased through a succession of values. There are a lot of different terms here that needs to be paid attention to. It's a chaotic solution, so that points towards the irregularity. It's three-dimensional, so turbulence we are saying is 3D. By definition, we are saying it is 3D. It is not 1D, it is not 2D. We are using the Navier-Stokes equations in this definition, meaning the Navier-Stokes equations mathematically describes turbulence. Obviously, in the last class, I covered that, but this is based on this definition that we now know that the Navier-Stokes equations describes turbulent flows. Something new that is coming into this definition, sensitive to initial data, meaning it is sensitive to initial conditions. So any slight change in the initial condition will change the way the flow develops, will change the way the flow behaves, and which occurs as a result of successive instabilities of laminar flows. Successive instabilities. As the laminar flow, once you have laminar flow, and when you change a bifurcation parameter, when you increase a bifurcation parameter to be specific, what is that bifurcation parameter? It is the Reynolds number. as the Reynolds number is increased, you start to see instabilities in the laminar flow. This is what Reynolds observed. He had laminar flow initially when the Reynolds number was low. He started to increase the flow rate, increase the Reynolds number, and then he started to observe instabilities in the flow. So that is the successive instabilities of laminar flow. As a bifurcation parameters increase through a succession of values. So as you keep increasing the Reynolds number, you start to see instabilities in the flow, disturbances in the flow, which will eventually lead to turbulence. So this is now the modern definition of turbulence. Is this complete? No. But this is the definition that is used in the modern era. This came out of three different parts of the study of evolution: the statistic, structural, and the deterministic. Now, agreed, this definition is somewhat vague in the sense it is not like I'm saying again, it is not like a definition that you would see for other phenomena in classical physics. However, it still has specific elements that we need to pay attention to. And that specific elements allows us to examine these kind of flows in detail. So we talked about how the modern definition includes these specific elements. First one, it specifies the Navier-Stokes equation. So it acknowledges that the Navier-Stokes equations describes turbulent flow. And that was a big leap from the previous definitions because it did not have the Navier-Stokes equations in its definition. Second, it acknowledges the fact that the fluid flow is chaotic, like irregular, erratic. Irregular part was there in previous definitions, so it acknowledges that. But it also does not use the word random. It does say it is chaotic, but it does not use the word random. It is deterministic and random. How do we know it is deterministic? Even though the definition does not use the word deterministic, the fact that it is using the Navier-Stokes equations means it is deterministic, because the Navier-Stokes equations are deterministic, correct? They're not random. There's no random component in the Navier-Stokes equations. So in that sense, we are acknowledging that they are deterministic and not random. So this is in contrast to Heinz's definition, right? Heinz said specifically that there's a random variation of space and time. Random variation with space and time. But the modern definition does not include that. And this is overwhelmingly supported by experimental data. What was the next point? It uses the word three-dimensionality, three-dimensional. So turbulence is 3D. And that is supported by a whole discussion in Tennekes and Lumley's book where he talks about how vortex stretching plays a huge role in turbulence generation and propagation. Vortex stretching is a mechanism where the vortices get stretched and the large vortices are broken up into smaller and smaller vortices. This vortex stretching term is absent in the 1D and 2D vorticity transport equations. It is only present in the 3D vorticity transport equations. Hence, turbulence is a 3D phenomena and not a 1D or a 2D phenomena. Now, the 1D and the 2D versions of the Navier-Stokes equations do produce chaotic solutions, but that might be just chaos and they might be very different from turbulence. So that's a different discussion to be had, how chaos is different from turbulence. Nevertheless, 3D Navier-Stokes equations are the only ones that can describe turbulent flows. Now, finally, the requirement of sensitivity to initial data. That is an added point in this definition. And this is what allows us to distinguish between laminar flow and turbulent flow. So if you think about it, laminar flow, viscous diffusion dominates. So any disturbances could be due to disturbances in the initial conditions. Any disturbances are diffused by the viscous effects because viscous diffusion is dominant. Turbulent flow, on the other hand, convective transport is dominant compared to viscous diffusion. So any disturbances say due to change in initial conditions, even a minor change in initial conditions, tend to linger on and propagate or even start to amplify in a turbulent flow. That's the difference. So that sensitivity to initial data is very important in this new definition of turbulence. And it is one of the characteristics of turbulence, as we'll see soon. So based on this definition, based on our description of turbulence and different observations, experimental observations, we can list down a certain set of attributes of turbulence. And we'll cover all of this in detail in the coming classes. But the first one is the disorganized, chaotic, seemingly random behavior. Remember, it is disorganized and chaotic. We know that it is irregular. Others have described it as irregular, defined it as irregular, and we are saying it is disorganized and chaotic. But seemingly random, not random behavior, but seemingly random. So to us, it seems like it is a random behavior. Non-repeatability, the second one, non-repeatability. That's the sensitivity to initial conditions. So that means a slight change in initial conditions. And this could be due to anything, external factors, say impurities in the flow in an experimental setup. That could lead to a minor change in initial conditions. And the turbulent flow is sensitive to that. So in that sense, it is irrepeatable. Okay, you cannot repeat the same and get the same answer. Third one, extremely large range of length scales and time scales. So we talked about this at length. You have a large range, large scales and small scales, and you have a whole range, not just one set of large scales, one set of small scales. Large range of length scales, and due to that, a large range of time scales. Because the smaller scales will have different time scales than the larger scales. That's the third point. Fourth, enhanced diffusion. Again, this is also something we talked about, how the convective transport dominates over the viscous diffusion and leads to enhanced diffusion, turbulent diffusion, turbulent mixing. Keep in mind, when I talk about the range of length scales, it is the small scales are still larger than the molecular scales, much larger than the molecular scales, and the continuum hypothesis is still valid in turbulent flows. We started with that. So related to that, when I talk about mixing, turbulent mixing versus viscous diffusion, viscosity plays a role in both of these. The viscous diffusion being negligible leads to turbulent mixing dominating. And at the small scales, viscosity plays a role in the dissipation of the small scales. So we talked about this earlier, where the large scales break up into small scales into even smaller scales. Even Richardson in his definition talked about that, right? He mentioned that as you're getting into smaller and smaller scales, eventually those scales are going to dissipate because of viscosity. The three-dimensionality, the time dependence, the rotationality, this is the fifth point. The three-dimensionality, time dependence and rotationality. So the rotational part is also something to keep in mind. Remember, you have potential flow, which assumes irrotational flow that cannot be turbulent. Okay, the rotational flow, the turbulence is characterized by rotationality. 3D, of course, and it is dependent on time. And finally, intermittency in both space and time. This is also a concept we cover in detail. It is related to the percentage of time a flow exhibits irregular temporal behavior at any selected spatial location. So how long does it stay irregular? That determines the intermittency. Does it stay irregular only for some periods of time and immediately comes back to being regular? Then that wouldn't be classified as turbulent. So a simple example would be if I record the velocity at a certain point and the velocity shows this. That means, what is it telling me? It is telling me that the velocity was irregular only for a very short period of time. After that, it was just regular. This the extent to which it stays irregular determines the intermittency. Generally, in a turbulent flow, what you see is this, as opposed to this. This is more like the second one. The bottom one is more like transitional flow. Okay, so I hope that was clear. We will continue with in the next class by talking about a history of turbulence and how different people were able to come up with different theories of turbulence, starting right from the 1900s to now. Thank you.